Okay, welcome to lesson 9. It's the last lesson for trigonometry. We're going to talk about sinusoidal applications. So a couple things you're going to have to be able to do is if you're given an equation, just describe the periodic situation. So we've already seen a little bit of that. And then we've also seen this, if you're given a situation, then make sure that use the key features to potentially come up with the graph and the equation. So as a warm-up, we actually want to look at sinusoidal functions in the real world. And so we're going to look at a quick video here from YouTube, and you can look at both of these links. The first one has sound. It's really neat. We're just going to look at the second one. And so this is just what we call a timescape, time lapse. So it's 100 billion liters twice a day, liters of water twice a day. This is the Bay of Fundy. So you notice the people walking as the sun comes up, and then the tide comes in throughout the day. And this actually happens twice a day. So you can see how deep these waters get. People turn into rowers and they try to row in. And they get up to a certain depth on the rocks, and then the water goes back down. And so you can just see the water filling up the bay. And so the water is actually coming all the way into the bay, and so even out here is actually getting deeper and deeper. It's probably one of the more impressive natural wonders that Canada has. Niagara Falls gets all the glory, obviously, but the Bay of Fundy is just really an interesting thing. And so and the other video actually talks about the depth of the water going between 400 and 700 feet at certain points. And so if we talk about this as a periodic sinusoidal function, and so, sorry, the video started behind. A real life sinusoidal function, you talk about this example, and so we think about a point out in the bay, and really the x variable would be time, the y variable would be the depth of the water. And so as the time increases, the depth of the water will rise and fall. And this actually follows a nice sinusoidal pattern. There's a lot of sinusoidal patterns in the real world, and we'll see 3 today as we go through the examples. So here's one that's a little bit conjured up, but very interesting nonetheless. It's jobs available in a week, and so this is the model since the start of 2014. And so we look at the key features. The period is 5.56 if we divide 360 by horizontal compression factor. And the quadrant, so what it goes up by every time, is 1.39. That's why I set the scale here for the graph to be every 1.39. The amplitude is 4.1. That's the vertical stretch factor. And the axis is 5.8. That's the vertical shift factor. And so we draw that middle line, the axis, the maximum, by adding 4.1, the amplitude, to 5.8, and subtracting it from 5.8, we get 1.7. And then since this is a sine curve, we're going to start in the middle and go up. And so we get this basically as our sine curve. And by being able to model it, we can now answer the questions. It just helps you see the picture a little bit better. Most jobs available at a given time, you can see, is 990 jobs. Just go back to what J represents. It's the jobs available in hundreds. Which week will jobs be at their lowest? At week 4.17. So 4.17 somewhere in February. And every 5.56 weeks after that. And what the lowest is 170 jobs. How long does it take? 5.56, so about a month and a half to go through a job cycle. And the average jobs available is right in the middle at 5. Okay. Our next application, we're actually going to look at data that's not the nicest data. As we graph it, the points are not perfect, but they do follow this sine curve. I chose to let January be month 1. It probably might be better to let January be month 0, but it just as long as you specify what X represents, X would represent the months how many months have passed or the end of the month. Would use the sine and cosine model. Since we're not letting January be month 0, it doesn't really matter. It's really up to you. You both have to require horizontal shifts. If you let January be month 0, you don't have to horizontally shift the negative cosine curve. But knowing that there's a 12-month period and every 3 months, that just tells you the shift. So if you're going to use a negative cos curve, we got to shift 1 to the right. If you're going to use a positive cos curve, we got to shift 7 to the right to start here. If you're going to use a positive sine, we're going to start here on the axis going up, and we're going to shift 4 to the right. So looking at the equation, we're going to take an amplitude of approximately 18, because we're going to call the period 12 months. We're going to call the axis approximately 0. That's not maybe the best way to find the axis. The best way might be to average the max and the min. However, I wasn't really comfortable with that because I noticed that each quarter, so every 3 months, we were still above 0 at 4 and 10. So I wanted to use at least 0 as my axis. Even though January was negative 18.6, which is lower than the max at 17, there's a little bit of gray area here rather than just averaging the max and the min. So I just use an axis of 0. Remember, it's a curve of best fit, so it's not going to be perfect, and it's for predicting. Horizontal compression, to get to 12, we have to divide 360 by 30. And so we figure that out by dividing 360 by 12. And so our equation looks like this. We've got the amplitude. It's a negative cosine curve shifted to the right one. Average temperature for month 20. If we sub in 20, we get 15.6, which seems to make sense. It's not the most elaborate predictor because it is a cosine curve. It's just kind of getting you an idea of what kind of things you could do with trigonometry. The reason why I say it's not an elaborate predictor is we could actually just say, well, month 8 is August, and so 12 months after that's month 20, so I'm going to predict 15.4. At least we know that our model was set up properly to get 15.6, which is very similar. So it'll be August the following year. You can get a lot more elaborate, and university can learn forecasting techniques to fit models using computers, and they could combine sine and cosine curves to actually get to take in account seasonality and changes year after year. Okay, our last example is the height of a flagpole just swinging back and forth in the wind. Swing back and forth 240 times every minute. Plus 10 is to the right, minus 10 is to the left. And we're going to start at 0 and then go to the right. That's what it's going to tell you. We really want to start by sketching a graph to see to get this equation. And so to do that, we actually have to look how fast it's going. And so if it's going, you have to figure this thing out. We just want to find out how long does it take to go to 10 to 0 to negative 10 to 0 again. And it's going to happen 0.25 times, or 0.25 seconds. So it'll be 4 times a second. In 1 second it happens 4 times. However you want to get that, but that's going to be your period. If you cut that period into 4 parts, we get 0.0625. And so we actually don't end up needing that number, but it helps to kind of draw a sketch that every 0.0625 and total in 0.25, we actually have a full cycle. The K value is found by dividing the 360 by the period, so you get that horizontal compression, which is obviously really big, of 1440. There's no vertical shift value, and the amplitude is actually is at 10 because there's a vertical stretch. And so the equation is pretty simple because there's actually no horizontal shift either. It's just 10 sine 1440x. The last one, it's kind of a big assumption, but if the wind speed slowed down a little bit and just made that amplitude, so it wasn't pushing it as far back and forth, it still kind of does a rotation. It still does one full cycle every 0.25 seconds, what happens is if you reduce it by 20%, instead of going 10 and negative 10, it's going to go to 8 and negative 8. And the only equation change is that instead of a 10, we have an 8. Okay? And so there's some practice questions to get you. Like in the first page, they say with technology you can use Desmos instead of a graphing calculator. And then these are practice where you actually have to come up with the equation.